Hello, I'm Adam Lander from EDG Consulting in Australia, and this is a presentation on the geotechnical assessment for alignment selection in the Australian High-Speed Rail Study. The Australian High-Speed Rail Study was undertaken in 2012 to assess a high-speed rail link along the east coast of Australia from Melbourne in the south through Sydney to Brisbane in the north. The study area was approximately 2,000 kilometres long by 200 kilometres wide, when you consider all the turns and twists along the alignment. And it was undertaken to develop a preferred alignment for future preservation and to assess the financial feasibility of the project. Alignment generation and selection was undertaken using the Quantum alignment planning software. And what this does is it utilizes GIS shape files for a whole lot of different constraints, whether there be urban planning, geotechnical, environmental, flooding, and the like, assigning unit costs for these, and then inputting the design parameters for the alignment. And for a high-speed rail line, the horizontal curves can be several kilometres in radius. For the geotechnical component of the assessment, we considered two main data sets, geology and mining. The third set, slope, was initially considered to assess landslide risk, but was later excluded to simplify the assessment as we had so many different constraints from so many different disciplines. So the big problem for us for the geotechnical assessment was how to characterise the ground conditions for a 2,000 kilometre long by 200 kilometre wide study area into meaningful units, and to do it within a 3-week time period. Well, the solution that needed to be digital, and we were fortunate to have seamless geology GIS data sets available for each state. So we broke down the ground conditions into 3 main units for engineering purposes: rock, soil, and soft soil. So rock comprised all rock materials in the engineering sense, materials that you'd be able to achieve steeper slopes, but excavation, it may be more difficult. Soil was all soil strength materials that don't require extensive subgrade treatment. Moderate slopes would be achievable in cuts, and materials would be readily excavatable. For soft soil, this comprised all deep compressible soils that would require extensive ground treatment for the settlement sensitive high-speed rail infrastructure. So on the first pass, there were many different geological units that were encountered throughout the study area. So we needed to work out a way of breaking this down. And we classified this initially primarily on geological age and lithology within the available GIS data set. But there were a lot of secondary factors we also included in developing an algorithm to automate the process and produce the shape files required as inputs to the alignment selection. So the challenges associated with developing this geology data set were that there were broad descriptors in the GIS data. Sometimes the age was very broad, maybe expanding tertiary to quaternary. In some areas, certain attributes were just listed as undifferentiated. There are also inconsistent descriptors across map boundaries, mapping undertaken at different times, and mapping undertaken for different states with different units, or with the same units at state boundaries being described differently. So this developed a few inconclusive units from this automated approach, and we applied some secondary attributes to those. So some of those, such as elevation data, was useful in assessing low-lying coastal areas that may have soft soils. And then we narrowed that down to a much smaller subset of inconclusive units, which were then able to assess on a case-by-case basis and allocate to one of the 3 main categories. We also did site-specific assessments for the approaches to each of the major cities and for certain major river crossings and topographic features. For example, to get off the Triassic Sandstone Plateau down to Wollongong, which is at sea level, through a very landslide-prone area, required a site-specific assessment. And this is kind of where we went from and where we got to. On the left is an excerpt from the 1 to 100,000 coastal geology near Taree in New South Wales, showing many different units. And on the right-hand side, the classified geology dataset file. For the mining, this was quite simple. It was broken down into past and future, known past workings available from Mine Subsidence Board, areas that would be considered to have a subsidence risk, and then future mining areas which may also have a future subsidence risk, but also may have a cost associated with sterilisation of the mining assets. For the alignment generation to work and for it to optimise, it needs to work on cost. So we prepared a whole lot of typical earthworks, retention systems, bridge foundation details, and they were used in the cost estimation for the project. And then also for each of the geology data sets, these dictated the form and extent of the earthworks. For example, the grades of the cut batters, the heights at which retaining walls would transition from a retaining wall to a cut. And they were entered as inputs or constraints within the alignment selection. Also for the soft soil areas, these were all provided with the cost of a viaduct as subgrade support to simplify the process. Past mining areas were assessed a cost based on remedial grouting programs from past projects, and future mining areas, due to the different costs associated with the different types of mining, were assessed on a case-by-case basis. In conclusion, it was the combination of the digital data and the use of the algorithm combined with engineering geological principles, which enabled a large study area to be rapidly assessed and classified in a short period of time. The delineation of soft soils presented the major challenge for the assessment, and the exclusion of the slope data set was considered potentially problematic. So we followed up with that with specific assessments for key areas. Thank you.